In this video, I'll explain to you how to apply temporal filtering and normalize your data. Let's talk about temporal filtering first. Temporal filtering is a good way to remove constant noise in your data, such as heartbeat. Those signals are present during your entire experiment at a specific frequency. For example, around 1 Hz for the heartbeat. Temporal filtering allows you to remove specific frequencies in your data. The first thing to know is that any signal can be decomposed into a sum of sine waves of different frequencies. This is called the Fourier transform. The result of the Fourier transform is the frequency spectrum of the data, which you can see by clicking on the frequency spectrum icon right here in the toolbar, and you can expand it like so. If your data has a good signal quality, you can immediately see a peak around 1 Hz, corresponding to the heartbeat. You can then decide which frequencies to remove with temporal filtering based on the noise frequency you see on the frequency spectrum. There are 2 types of filters available in Satori: low-pass filters and high-pass filters. Low-pass filters remove frequencies above the specified cutoff frequency. In other words, they let lower frequencies pass. High-pass filters remove frequencies below the specified cutoff frequency. In other words, they let higher frequencies pass. Please note that the filter will not distinguish between 2 different sources at the same frequency, so you have to be very careful that no signal of interest, which is in this case the hemodynamic signal, is present at that frequency. Also, the filter will remove the specified frequencies for the entire duration of the recording, so this method is more appropriate for constant background noise and not for spikes or baseline shifts. To set up temporal filters in Satori, go to Analysis, then NIRx Data Preprocessing, and check temporal filtering, the temporal filtering box in the physiological noise removal section. To specify the type of filter you want to use, click on the Advanced button, and then in the temporal filtering section, you can select among 2 types of high-pass filters and 2 types of low-pass filters. You can specify the cutoff frequency of each filter on the right in Hertz. To determine which type of filter to use, you can apply each of them to your dataset to see how they work before selecting one for your final analysis. Lastly, linear detrending allows you to remove slow drifts in your data. Now let's talk about normalization. Normalization allows you to put all the signals in your dataset on the same scale. This is very useful when you have regions with signals of different amplitudes due to peripheral tissue properties, for example, or participants with different amplitude responses. Basically, you want to make sure that a participant with weaker signals than the others will not attenuate your results. To overcome this, you need to normalize the data. In Satori, this can be done by transforming the data to z-scores or percent signal change, PSC. Z-transform expresses the data in standard deviations above or below the mean instead of concentration values. In each channel, Satori will compute the mean and standard deviation of that channel in order to calculate the distance of each time point to the mean. For example, if a time sample has a z-score of 2, that means that this time sample is 2 standard deviations above the mean of that channel. Z-transform preserves the shape of the time series, so the hemodynamic response will have the exact same shape as it did before the transformation, only its size will change to match the scale of the responses in other channels. Percent signal change is similar to Z-transform as it expresses each time point as its distance to the mean, but instead of standard deviations, it expresses the change in percentage relative to the mean. For example, a data point with a value of -8 means that this data point is 8% below the mean. As for Z-transform, PSC transform doesn't change the shape of the data, it only changes its scale to make it comparable across channels and participants. So we can see that here. And that's all for temporal filtering and normalization. See you in the next video.